Okay, here we have a humidity problem that involves tracking the humidity, relative and absolute humidity changes of an air mass as it rises over a mountain. And this is a really good exercise to make sure you understand how to read the saturation or the absolute humidity saturation curve diagram. So our air coming in reaches is at sea level. It's got a temperature of 25 degrees C, and we're told its absolute humidity is 15 grams of H2O per kilogram. And the first thing we want to do is plot that point up and determine its absolute humidity. So we're going to go to the absolute humidity diagram. Let's see, where is that one? There it is there. There it is. And we're at, what did I say I was at? Holy cow, I forgot already. I'm at 25 degrees with 15 kilograms of water. So 25 degrees and 15 grams. So 25 degrees and 15 grams of water vapor per kilogram of air. So that's where we plot on the diagram. Remember that the relative humidity is equal to the absolute humidity divided by the absolute humidity at saturation. And so that will equal our absolute, we were just told the absolute humidity is 15. That's again grams per kilogram. And if I read my diagram here, the saturation value is up here, right? And that looks like to be 20 grams. So this is 15 grams per kilogram divided by 20 grams per kilogram. I can actually do that in my head. That is 0.75 or 75% relative humidity. So I'm going to go back to, there we are, back to here. And whoops, and I'm going to write that in, right? So we're at 75. Oh, this is giving me hard problems, isn't it? We're at 75% relative humidity. And now this air is being forced up over mountains. And as it goes up over mountains, it's going to cool. Remember, the most important thing in this whole section is that cooling air eventually becomes precipitating air. Rising air is cooling air, becomes precipitating air. So let's see how that happens if we look at, let's see, there we go. So let's see, we're on layer 4. Okay, so we're gonna, so now this air, I'm just gonna use a different color here, right? So the air is going to rise. So there it is here. And it's going to rise, and as it rises, it cools. As it cools, the only thing that changes on this diagram is its temperature. Temperature is on the x-axis, absolute humidity is on the y-axis, and so the air mass, the condition of the air mass will follow a line that goes like this until it hits the saturation curve, right? And at that saturation curve, assuming that there are nuclei, precipitation will begin to form. And at that point, at this point right here, let's give it a different color. Let's give it a deeper red color here. So at this point right here, let's call this point B. Okay, at point B, the absolute humidity is 15 grams per kilogram, and the saturation value is 15 grams per kilogram. So at B, the relative humidity is going to be 15 over 15 over, or 100%, right? So it's 100% saturated, and it's going to begin to form rain. Now, so the question is, well, at what elevation does this happen? Because the air is going to rise, and eventually this is going to happen, and we need to know the elevation at which that happens so we can continue our problem. And notice that in order to reach that point of saturation, the air mass had to cool by 5 degrees. 5 degrees. And what you need to remember is that the adiabatic, the dry adiabatic lapse rate is 10 degrees C per kilometer, or equivalently 1 degree C, C per 100 meters of elevation. So in order to decrease by 5 degrees C, I hope you can see that the air must have risen by 500 meters. 1 degree C per 100 meters. So in 500 meters, it will have decreased by 5 degrees. So this little path here is equivalent to a 500-meter ascent. So let's put all that information that we just gathered into that first diagram here too. Okay, I don't want to see that one. There we go. So let's go back over here. Now, so we said that when we got to 500 meters was where saturation began, right? We're still at 25 degrees C. Oh no, we're not. We cooled down to 20 degrees C, right? We cooled 5 degrees. The relative humidity now, remember we're still at 15 grams of water vapor per kilogram of air. But now that's also the saturation level, so that our relative humidity is 15 over 15, or 100%. Okay, so we've reached the point where precipitation is starting to happen, but notice that the air is going to continue to go up, right? It's going to continue to go up another, well, at the summit's at 1500 and it's at 500 meters, so it's going to go up another, looks like 1,000 meters, or another kilometer. It's going to rise another kilometer before it can start going down. Now remember that once precipitation starts happening, now like if the air's rising, it reaches this point, and as it rises that extra kilometer, it's raining the whole time. And because it's raining the whole time, the wet adiabatic lapse rate is given by 6 degrees C per kilometer, or 0.6 degrees per 100 meters. And since this is working out really nicely, right, it actually rose an additional kilometer. So during that ascent, we can write in right away what its temperature must have decreased to. Remember, in that extra kilometer, it's going to decrease now at 6 degrees per kilometer. So the temperature at the summit here will be 20 minus 6, or 14 degrees C. There's a couple other things I know, but let's actually demonstrate that by going back to my diagram here. Okay, so this is my, there we are. So we're looking back on the diagram now. So we have come to the summit, and we're going to cool down to a temperature of 14 degrees C. 14 degrees C is over here, right? And all that time we are continuing to rain. And as long as we're continuing to rain, we are actually going to be following this curve, this saturation curve, all the way down. Right? We can't get to the left of it because we can't be oversaturated. And we can't get to the left of it because we're continuously cooling. So instead, we just sort of ride this saturation curve all the way down to the summit, which is reached right here at point C. Right? Remember we said the temperature is 14 degrees C. We cooled an additional 6 degrees as we rose that extra kilometer between B and C, and at point C we reach the summit. So again, since we're riding that curve down at C, we also know that we can say at C, same thing, the relative humidity is going to be 100% again, right? But now notice that at C, the absolute humidity has decreased because we're wringing water out of the air the whole time we're raining, right? So by the time we get to C, it looks like the absolute humidity is about, I'll just call it 10. It might be a little less than 10, but it's hard to see the way I've done this. So let's just saw the absolute humidity is about 10 grams of water vapor per kilogram. So let's put that information back onto our table here, right? Okay, so back here, we know that the relative humidity stayed at 100. Relative humidity stayed at 100%. We were just riding that saturation curve down, but the absolute humidity went down to, and I've already forgotten what it was. What was it again? It was down to 10, right? So this is down to 10. I'm still learning. 10 grams of water vapor per kilogram of air. All right. And we're almost done. So now what's going to happen is the air is going to spill down the other side and return all the way to sea level. Now we can do this calculation of temperature right here. Remember that the dry adiabatic lapse rate, let's write that down, is equal to 10 degrees C per kilometer or 1 degree C per 100 meters. And that occurs when precipitation isn't happening. And as we cross the summit and we start descending, the air mass, remember, will be warming. And as we warm, let's go take a look at this again just to make this clear. As we now warm, remember at this point we're warming, so our path is, let's do it in a different, this color is good. So as we go now, our path is moving like this, right? Let's use a different color. I wanted to use a different color. Like this, right? And notice that we're getting less and less saturated. We're going to the undersaturated side of the line, and that's not where precipitation happens. Precipitation happens over here somewhere or on the line. And so the air mass now is not raining. So if it's not raining, we're going to be descending at the dry adiabatic lapse rate, which is again 10 degrees C per kilometer, and we're going to descend 1,500 meters, and that should therefore increase the temperature by 15 degrees C. So we should go from 14 all the way to, what's that, 14 and 15 all the way to 29 degrees C, right? Like this. Did I do that right? 14 and 5, yeah, that looks about right. So we're descending 1,500 meters. So we're going to go all the way here to 29 degrees C, right there. Okay, and let's put that. And so our absolute humidity. Let's say now we're at point. Let's call this point D. Okay, so at D now, at D, the absolute humidity is staying the same. You can see we're just still at 10 grams of water vapor per kilogram. We're going to have to figure out the relative humidity in a second, but it's at 29 degrees C. So let's put that information into our. There we go. So let's put that in. So we go. So we're going to go 14 degrees C. We can write this down. Plus 15, we're going to go all the way to 29 degrees C back at sea level. And our absolute humidity stays at 10 grams per kilogram. We're not wringing any water out of the air because the air is not raining, right? So the only thing left to do is to calculate the relative humidity, and I think by now you know how to do that. So let's go look at the diagram here. So we want to know the relative humidity at D. Let's pick yet another color here. How about bright greenish? Okay, so here's D, right? It doesn't like it when I do that, does it? Okay, there it is right there. Okay, so the relative humidity is going to be, remember, it's equal to the absolute humidity divided by the absolute humidity at saturation. And the absolute humidity we just said was 10 grams per kilogram of air. And we have to sort of read off now what the absolute humidity at saturation would be. That's way up here. That looks like about 26, right? So the relative humidity at 29 degrees C will be 10 divided by 26, which is about 38, 39 maybe percent, 0.39 or 39%, equivalently saying it in different ways. So the relative humidity, final relative humidity will be, let's just call it 39%. So let's go back and write that into our diagram here now. So final relative humidity is 39%. And that's pretty interesting, isn't it? So the air has gone up over the mountain. Its relative humidity has gone from 75% to 39%. The air is much drier. The absolute humidity has gone from 15 grams per kilogram to 10 because it lost all that water by rain on the front side of the mountain, right? And the air has warmed tremendously, right? It came in at 25 degrees and now it's at 29 degrees. And where did that heat come from? Well, that heat actually came from the latent heat of evaporation. As that water precipitated, as that water vapor changed into water, it gave off heat, which warmed the air. So that's why the air is warmed up, and that's why the air is drier. Also, let me make a quick comment here. This is exactly why we get rain shadows, right? So you've probably heard of this before, but basic idea is, let me just, so if we have, this is the coast like this, and there's my mountain, right? And my air mass was forced, it came in like this, and it was forced up, up, and then over. And as it was forced up, it hit some elevation, right, where it began to rain. And then it rained continuously in this region here, right? And so the front side of this mountain, the one facing the wind's coming in this direction, right, is the wet side of the mountain. And on the back side of the mountain, as the air has already been sort of wrung out, and now coming down, remember the air here is warming air, and warming air is drying air. So on the back side of the mountain, we end up with very dry conditions, low humidity, and this is called a rain shadow. And this would be where our rainy side of the mountain is. And in places like Washington, the difference is Washington State. The difference is dramatic between the wet west side of the mountains and the dry east side of the mountains, caused by this orographic precipitation.